Assalamu alaikum. In this lecture, we are going to cover a few topics related to DC motor. Uh, in our previous classes, we have already discussed a few topics related to DC motor. For example, we have talked about back EMF, which is involved with the DC motor. We have talked about how they are generated, how they basically governs the function of a DC motor. Then we had a discussion about torques associated with DC motor. We talked about armature torque, shaft torque, how shaft torque is connected with the output power of a DC motor. So in this lecture, we will move beyond those topics. We will discuss some other topics that we haven't discussed so far. And from this discussion, we have set the syllabus for your quiz number 3. Okay. If we look at the overview of the contents that are going to be discussed in this lecture, they can be classified in this way, that we will first talk about classifications of motor, and then we will learn about some equations related to speed of a DC motor, and at the last part we will look at the diagram of power stages of a DC motor. In terms of classification of motor, they are pretty much similar to the classification of DC generator. As we already know, for DC machines, be it a DC generator or DC motor, they both have similar working principle. They have similar constructions. So like you have already studied about the types of DC generators, so the types of DC motors are also the same. They can be classified into 3 wide classes. One is shunt wound motor, one is series wound motor, and another one is compound wound motor. So let us look at the shunt wound motor first and the features it involves. It says that the field winding is connected in parallel with the armature, which is true. Here the shunt field winding is connected in parallel with our uh, armature and the supplied voltage, and the current through the shunt field is not the same as the armature current, which is also true. If you look here, there is a junction, so the current that is going into this junction gets divided into two parts. So here we get shunt current and here we get armature current, and we want our armature current to be as high as possible. So in order to maintain that, our shunt current should be as low as possible. If we want our shunt current to be as low as possible, to make that happen, we should keep our resistance of the shunt field as high as possible, which is written here, that shunt field windings are designed to produce the necessary mmf by means of a relatively large number of turns of wire having high resistance. So in turns, what happens in this type of motor, that there are two current involved. One is shunt current and one is armature current, as the working principle of motor demands armature current to be as high as possible and shunt current to be as low as possible, and that's why the shunt field is designed in such a way that they are high in resistance and they are capable enough to generate the magnetomotive field or magnetomotive force that is required to rotate our uh, motor. So that was uh, shunt wound motor. Then let us have a discussion about series wound motor. Okay, in our series wound motor, the series field is connected in series with the armature. So the current that is flowing through the shunt field and the current that is flowing through the armature is the same current, and as our working principle demands, the armature current should be as high as possible. So but the same current is flowing through the series field also. So to maintain this thing, we should be careful about designing our series field, and we should design our series field in such a way in series wound motor so that the resistance of this series field is as low as possible. So the same thing is written here. Since the current passing through a series field winding is the same as the armature current, series field winding must be designed with fewer turns so that it shows low resistance. So that is the basic difference between the shunt wound motor and series wound motor. And why we have talked about armature current, we will find it out later in the later part of our lecture. There are other type of motor available, that is compound wound motor. In compound wound motor, there are also two subtypes. One is short shunt connection and another one is long shunt connection. In short shunt connection, the shunt field is uh, practically connected in parallel with the armature, and whereas in long shunt connection, the shunt field is connected in parallel with the armature, also the series field. So that is the basic difference between short shunt connection and long shunt connection. Uh, we won't have much discussion about compound wound motor. So from this part, only these two, by knowing only these two subtypes of compound wound motor will be enough for us. Our main focus will be on the series wound motor and shunt wound motor. So if I run a summary of what we have discussed so far, that there are three types of DC motor. Among them, two prominent types of DC motors are shunt wound motor and another one is series wound motor. In shunt wound motor, the shunt field is connected in parallel with the armature. So, and in series wound motor, the series field is connected in series with the armature. So, what it implies that in terms of shunt wound motor, the magnetic flux that is generated uh, is remained constant across armature, as shunt field is responsible for generating the flux and they are connected in parallel. That's why the flux can be considered as a constant value. And in series wound motor, what happens, the shunt field is connected in series. As the current is varying here, the flux is also varying, so we will consider our flux available here is proportional to the armature current. And what we considered as a constant in shunt wound motor, we cannot consider the same thing for series wound motor. So the major takeaway from these two types of these two classes of motor is that the differences between the relationship between flux and the armature current. In If I summarize the statement here, for series wound motor, we have our flux proportional to the armature current, and in shunt wound motor, we have our flux not connected with the armature current, rather the flux remains most of the time constant. So in the later part of our lecture, this two information will come handy. So we have talked about classification of motor, and now we will have a look at a few equations that are related with the speed of a motor. Okay. So far in our previous lectures, we have learned about back EMF. So look here, this is back EMF, and we know the formula of, or the equation of the back EMF is this. Also, we learned that back EMF can be described using this equation. If we equate these two equations, we get this thing, and from here we can rewrite speed of DC motor as a function of this thing. So here 60 A, P, Z, these things are constant, they are taken as a constant value here, and finally we have N constant into V minus IRA divided by phi. But we know that V minus IRA is back EMF, and by replacing EB here back into this, we get this thing. So the final line we have for the speed of a DC motor is that it is proportional to our back EMF, and the speed of motor is inversely proportional with the generated phi. If you remember, we have seen similar relationship with armature torque in our previous lecture that said that armature torque is proportional to phi I. Okay. So that is our takeaway from this speed equation of a DC motor. It says that speed of a DC motor is proportional to back EMF and inversely proportional to phi. So using this uh, we can establish a few more equations that will lead us to some numerical problems in future. So if you look here, from the equation that we have just learned, that is speed of motor is proportional to back EMF and inversely proportional to phi. So let's say we are running a motor at state 1, let's say at t is equals to 1 second, the speed of the motor is n1, and that is proportional to obviously some back EMF, and let's say at that time the back EMF is EB1, we have stated it, and the flux that was available we have stated it as phi 1. And let's say we are considering our state of the motor at, let's say, t is equals to 10 second. So obviously as the time progressed, the speed of the motor obviously changed. Let's say at that point the speed of the motor is, let's say, n2, and if we go by this equation, at that time it is proportional to, let's say, some other back EMF EB2, and that is inversely proportional to some other available flux there, that is phi 2. So we can state that at different time point or at different time instances, this relationship can be written as, let's say, n1 is proportional to eb1 by phi 1 and n2 is proportional to eb2 and divided by phi 2. Since these two statements are written as proportional, and we know that proportional sign can be omitted with a constant, and then if we take a comparison, we can come to a formula like this. I think if you just rearrange it, uh, you will be able to come to this point. So it says that if we are comparing speed of motor at two different instances, that speed at uh, second instance divided by speed at first instance is equal to eb2 by eb1 into phi 1 by phi 2. Okay, so this statement is true for series wound motor, but for shunt wound motor we know that phi is constant. So if at first instance uh, the flux available at the motor was phi 1, and at, let's say, at the second instance the flux available at the motor was phi 2, both of these phi would be the same for a shunt motor. So this ratio would mean 1. So if we translate this equation for shunt motor, so this is what we get. And for series motor, we can derive it in a different manner. As we know, for series motor, the phi is proportional to armature current that we have mentioned a bit earlier. So this phi can be replaced by Ia, and thus this formula can look like this. So for series motor, this has another variation, but if we replace the flux with our armature current, and for shunt motor, uh, the speed relation of a DC motor turns out to be something like this. So these formulas will be very useful for us in solving several numerical problems that are associated with DC motor. Now we have another formula named speed regulation. I think by now you all know what is speed regulation formula is. This is a comparison between full load speed and the difference between full load speed and no load speed. Obviously at no load the speed will be higher, at full load the speed will be lower. So there should be a difference between them, and if we compare it with the speed available at full load, we get the speed regulation. So this is another this is a parameter that helps us know how better the device that we are observing is functioning. So we have already seen in our transformer case we had a parameter like voltage regulation, and for DC motor we have a parameter like speed regulation. So speed in order to calculate speed regulation we need two values. One is no load speed, one is full load speed. If we have these two values we can always calculate the speed regulation of a DC motor, and this speed regulation is a parameter that shows how well our DC motor performs. So from the topics we have covered so far, it is apparent that the speed of our DC motor has some connection with magnetic flux. And in our previous class, we have learned that the torque of a motor has some relationship with a magnetic flux. But the interesting part is, if you look deeper into it, they both these two parameters both have relationship with magnetic flux, but they are in reverse order. How? A few moment ago, we have learned about the relationship between speed of motor and flux, and there we established that the speed of motor has a relationship with the magnetic flux, but it is inversely proportional. And in our previous class, we have seen that the torque of the motor has some relationship with our magnetic flux, but that is proportional in order. So that implies that if we make some change in terms of flux in a DC motor, that let's say if we have decreased the flux, that will increase the speed of the motor, but in return the torque will decrease. But if we look at it from a different perspective, the rotation that is involved in a motor is a mechanical thing, and if any body is rotating, it requires some mechanical power that we are defining in terms of torque. That means if we are applying some torque to rotating body, it will start rotating. That means after applying torque, it will have some rotational speed. So from this perspective, if we apply torque, we get speed, and which implies if torque is increased, the rotational speed should increase, or the other way around. If the rotational speed is increased, that means we have uh, added torque here. So these two should have a proportional relationship with them. But from the theory that we have learned, that gives us completely different idea. It says that these two parameters should be inversely proportional. So what is actually happening? But in practical case, if you think about it, in practical case, uh, this is the actual scenario, that if we are applying some torque to it, we will get some speed, I mean some rotational speed. So they two should work with hand in hand. But in our in the process that we have learned, that both have some relationship with the magnetic flux, and they are in reverse order. So what actually happens in practical case? Let us look at it from this portion of the slide. Okay, so let's say we're talking about a test case where the magnetic flux is decreased in the motor by decreasing the field current. So as we are talking about decreasing the magnetic flux by decreasing field current, that means we're talking about obviously shunt motor. We have a shunt motor here, and in this shunt motor we have decreased the flux by decreasing the field current. So that will have some impact. That means decreasing the flux will eventually decrease the back EMF. Why? Because back EMF has a relationship with the flux, and that relationship can be seen here from this formula. Is it okay? Uh, if we decrease the flux anyhow, that will decrease the back EMF. And if the back EMF is decreased, what impacts it has on, let's say, on armature current? It will increase the value of armature current. Why? Because back EMF and armature current has this type of relationship. If you look here, if the back EMF is reduced, that will increase the armature current. Okay. So in a practical case scenario, what we have done, we have decreased the flux associated with the DC motor, and in return, what we are seeing strong in terms of armature current. That means we have decreased a small amount of flux, but we have seen huge increase in armature current. But we also know that torque in a motor is proportional to phi Ia. As torque is related with both the quantities, one is decreasing, another one is increasing. Which one should be the governing one here? If you look at the picture, the Ia is the governing parameter here. That means the decrease of flux doesn't have much impact, whereas the increase in the armature current has much impact on the torque. So eventually what happens, as the armature current is increasing, very rapidly or in very the increment in armature current is very high, so that is why the torque is basically increased. As the torque is increased, so that basically results in increment in our speed of the motor. So the same thing is written here in text. I think if you go through the lecture or if you go through this part in text, you will understand the interesting phenomenon that takes place between torque and the speed of a DC motor. So that was the topic that even though our speed of the motor and torque of the motor has counteractive relationship with flux, but in practical cases we get to see the increment in torque is basically uh, helps us helps the motor running faster. So, so we can summarize it in this way. So now we will discuss about the power stages of DC motor. In your DC generator part, you have already seen similar type of a diagram, and for DC motor, the power stages are also very similar. So if you look at the diagram, it says that it has three stages. The stage 1 or A is the stage where we are taking input for the motor, that is the voltage applied to the motor into the current that is going into the motor. So that is the motor input we are giving, and from this input we are basically getting the mechanical power in terms of armature torque, and that is EBIA that we have already discussed in our previous class. And in the meantime, some losses occur, that is copper losses. I think you will know what is copper losses and how this is generated, and what is the and how we can basically calculate these losses. At the stage 3, I mean at the stage B, the motor starts rotating, and as some machine starts rotating, we have some losses related to iron and friction losses. So if we discard these losses from the power available at power stage B, we get the final output at stage C, that is motor output. So the overall efficiency can be calculated if we take a ratio of the power available at stage C divided by the power that we provided at stage A. The electrical efficiency can be calculated by the power available at stage B by taking the ratio with the power that was given to the motor at stage A. And the mechanical efficiency can be calculated by taking the ratio of the power available at stage C divided by the power available at stage B. So that was the basic overview of the power stages diagram of DC motor, which is very similar to the power stages diagram of DC generator. So that was the basic theoretical discussions of this lecture. And based on the topics that has been discussed in this lecture, I have added a few numerical problems that you can solve using the equations that have been discussed here. So if you go through the slides, you will find out these problems. So you can expect to have these numerical problems or the theoretical issues that has been discussed in this lecture in your quiz number 3. So that was it from my side for this lecture. Thank you very much.